Next section in chapter number 9, section 9.2, dual graphs. Dual graphs. What is dual graph? Dual means number of region or faces is equal to number of vertices, number of regions or faces. See these two pictures. One is denoted using phases, phase 1, phase 2, phase 3 and phase 4. Here 4 phases. Here we denote the another method, P1, P2, P3, P4, that is 4 vertices. Then a plane graph of G or partitions. Here P1 denotes by first partition 1, P2 partition 2, P3 partition 4, P4 partition 4. From this graph, here 4 phases F1, F2, F3, F4 and G star. Here P1, P2, P3, P4, 4 partitions. Then the rest of the plane into number of connected regions, phases. Regions means phases. See this graph. First we draw P1 to P2. That means partition 1 to partition we connected a vertex. That is here P1 to P2 connected a vertices. Next P2 to P3, that is adjacent. P2 to P3 is also adjacent. P1 to P3 is also adjacent, and P4 is outside, that is adjacent to P3, P1, P2. Okay, then P1 connected to P2, P1 connected to P4, P1 connected to P3, then P2, P4, P2, P3, also P3, P4, connecting these edges, because from the graph the adjacent partitions, that is P1 to P2, P2 to P3, P1 to P3, P3 to P4, etc. Like this, we connected all these graphs using vertices. That is called dual. Here this is the dual of the above graph. Okay, this is the dual, that is P1 to P3, P1 to P4, P4 to P2, P2 to P3, etc. P4 to P3. Here these partitions P1, P2, P3, P4 all adjacent. Then we connected using edges. Rest of the graph, that means the remaining graph, is called dual. This is the dual of the above graph. Okay, see this graph. From this graph, graph G has 1, 2, 3, 4, 5 faces. Okay, then we draw the adjacent partitions using edges. Okay, first from the figure G star, we know that F1, see F1, this is F1. From the above figure, see where is F1. F1 is outside of the graph. F1, it is one vertex, so F1 is adjacent to F1. Okay, F1 is adjacent to F1, so we draw F1 is adjacent to F1, that means a circle or a loop. Next F2, here this is F2. F2, its adjacent partitions are F1, F3, F4, F5, F3, F4, F5, all are adjacent vertices. See, F2 has adjacent partitions F1, F5, F4, F3. Okay, then see this figure, second figure G star F2. F2 this is F2. Okay, F2, this is the F2. This point is here F2. Okay, F2, here F2. F2 is adjacent to F1, F3, F5 and F4. So F1, F2 is adjacent to F1. Next, F1 is adjacent to F5. F2 is adjacent to F5. Next, F2 is adjacent to F3. F3. Here, next F2. Where is F? From the above graph, we know that F2 is adjacent, this is adjacent, this is adjacent, this is 4 adjacent, but here this vertex is separated to F2 and F4, that is not adjacent. Okay, therefore F2 is connected to F5, F1, F3. Okay, next we choose F3. Here this is F3. Okay, this is F3. See the second graph, F3, this is F3. So F3, that face is adjacent to F2, F4 and F1. Okay, F3 is adjacent to first F1. Next F3 is adjacent to F2. Next F3 is adjacent to F4. Okay, F3 is adjacent to F2. F3 is separated to F2, F4 and F1. Okay, next we take another vertex or another partition F4. Where is F4? F4 is inside. This is F4. It is clear that F4 is adjacent to F5 and F3. Okay, therefore the second graph or the dual graph F4 is connected to F3 and F5. Okay, next F5. Actually, from the first graph, F5 is here. It is clear that F5 is separated to F1. F5 is separated to F1, F2, and F4. Okay, F5 is separated to F1, F2 and F4. Therefore, from the second graph, F5 is connected to F4, F2 and F1. Okay. From all these vertices, after completing this graph, we get the dual of G, and the dual is called G star. Okay. One more thing, that here F1 is connected to F1, or F1 is separated to F1, also F1 is separated to F2. F1 is separated to F2. So from this graph, F1 is connected to F2, F1 also F1 is connected to F2. Okay. The remaining all these graphs, or joining all these, you get the dual of this graph. Okay. Next, theorem 9.3. Let V be a vertex of a planar graph G. Then G can be embedded. Embedded means planar in the plane in such a way that V is one of the exterior face of the embedding. Okay. A planar graph has V is the exterior face of the plane. Okay, ext V. Proof: consider an embedding G dash of G on the sphere. Such an embedding exists by virtue of theorem 9.2. We know that theorem 9.2 says that a graph G is embeddable in the plane if and only if it is embeddable on the sphere. It is embeddable on the sphere. You know, the sphere has some elements, that is, consider a sphere S resting on a plane P and denoted by Z. Then the point of S is diagonally opposite the point of contact S and P. So from 9.2 says embeddable in plane if and only if it is embeddable on the sphere. Okay. Then let Z be a point on the interior of some face containing V. Interior of some face containing V, and let pi of G dash be the image of G dash under stereographic projection from Z. Clearly, pi of G is planar embedding of G of the desired type. See this figure. This figure is stereographic projection. Here this is Z, one of the pole of this sphere. Therefore, the sphere S, consider a sphere S resting on a plane P and denoted by Z. That is, P is denoted by, this plane is denoted by Z. Therefore, it is embeddable on the sphere. It is embeddable, that is, it is embeddable on the sphere. G is embeddable. Here G is embeddable. From our theorem, new theorem says that pi of G star B is the image of G dash. Pi of G star is the image of G dash under stereographic projection. This is using stereographic projection from Z. Then clearly pi of G is a planar. Pi of G is a planar embedding of G of the desired type. Okay.